Here I thought I would show you how to do 3 problems in real analysis. These problems are ranged from easy, medium to difficult. These problems were either homework problems given to us during my time in my analysis courses last year, or they showed up on old qualifying exams. So I need to take the qualifying exam in August, so these videos where I do problems are supposed to provide a resource to help me review for the exam quickly, as well as help anyone that's interested in doing problems in analysis. Anyway, so let's do them. I'm going to do 3 in this video. So the first one is supposed to be an easy problem, the second not as easy, and the third, I won't call it hard, just harder, the hardest of the 3. So let's start with the first one. We want to prove that the following set is closed. So it's the set of all y such that the distance between x and y is less than or equal to some r, some positive r. And looking at this, it's kind of clear that this is supposed to be the closed r ball centered at x with radius r. And it's called the closed ball because it's a closed set, but we need to show that it is closed. So that's what we're going to do. Proof. One way to show that a set is closed is to show that the complement is open. So this is what we'll do. We're going to show that the complement is open and then just use the topological definition to show that our set is closed. Okay. So how do I show something is open? Well, we want to pick a point in the complement, put a ball around it, and show that that ball is contained in the complement. So let Z be an element of the complement. And now we need to find a radius small enough such that the ball is contained in it. So choose S positive such that something happens. So what do I need to happen? Well, I'm going to draw a picture. So here's the center. Here's the radius. So the complement is the space outside of this disk that I've drawn. And the idea here is that here's my Z in my complement. And I want to put a ball around him such that the ball is contained in the complement. And it has radius S. And I need to choose my S in a nice way. So it looks to me that I need this ball to be not touching this ball here. So if this is R and the distance between X and Z is just dxz, I just need to choose S smaller than this distance minus R. So I'm going to choose S such that R plus S is strictly less than the distance between X and Z. Said another way, we want S to be less than this value. And so now we will show that this ball is contained in the complement. So claim the S ball centered at Z is contained in my complement. So we pick a Y that's in the S ball. And then by definition, this means that the distance between Z and Y, I'll write it this way, the distance between Y and Z is less than S. And what do we know? We also know that R plus dy Z. So we take this value here and add it to, well, I guess in my picture, I'll draw my Y so that this is the distance between Y and Z. My picture's not very good. But we'll go through the logic here. So this distance is supposed to be less than the distance between X and Z. That should be clear. And then what do I know? I know that R is less than the distance between X and Z minus the distance between Y and Z. And then by the triangle inequality, that's less than or equal to the distance between X and Y. So I'll write by triangle inequality. But look at what this says. This says that r is less than the distance between x and y. And by definition, that means that y has to be in the complement of the closed R ball. Hence, this set is open, which gives us the result. So something like that. I'm always concerned about this statement here because it doesn't feel right to me. But if I add this piece over, it does become the triangle inequality. In fact, when I was looking over this problem I had before I made this video, I was like, am I sure about this? But I think it's correct. Correct me if I'm wrong, but this is just triangle inequality. All right, so that's the first problem. This was like the very first homework problem we were given in my graduate level analysis class. And I remember doing it as like one of the last problems in my undergraduate analysis course. And that line there that I just showed you always gave me a little bit of a pause. Okay, so question number 2. We have a Borel measurable function from the unit interval to r. We know that f is bounded below by 1 for any input. We know that the integral from 0 to 1 of f is 2, and the integral from 0 to 1 of f squared is 5. We want to prove that the integral of f cubed from 0 to 1 is bounded below by 14. Okay, this was a qualifying exam problem that appeared, it wasn't the first problem. The first problem is always a theorem. But if you ignore the theorem on those tests, then this was the first problem. And this was on the May 2022 qualifying exam. And that one, in my opinion, was the easiest one in the last 5 years. The problems on it were relatively simple, and this one was, I think, supposed to be the easiest one on the test, but maybe second easiest. I think there was one on there that was easier, but whatever, we'll do it. Now, I've done this problem so many times, and I've memorized the trick in it because there is a trick that's necessary in order to solve it. And if you don't see the trick, you kind of get stuck. Okay, so what's the first thing I notice? So I notice that f is bigger than or equal to 1, which means that f minus 1 is bigger than or equal to 0. And now I make an important observation. If we square this guy, that's the same thing as taking the 1/2 power of him, multiplying by him to the 3/2 power. Now, why on earth do I write it this way? There's no reason for me to write it this way. The reason I write it this way is because I'm going to need to use Cauchy-Schwarz inequality. So by the Cauchy-Schwarz inequality, I know that if I take the integral of this guy and square him, sorry, I'm fixing my paper. I know that's going to be less than or equal to the integral from 0 to 1 of f minus 1, forgot my dx, times the integral from 0 to 1 of f minus 1 cube dx. Because if you remember what Cauchy-Schwarz says, when I take the integral of this and square it, I don't have to square it over here. I could take the 1/2 power here and here, but I just simplified it by putting the square there. But you need to square the arguments. So the way I've split this up this way is that I square each of these guys to put them down here. And when I square this guy, I get f minus 1 to the 1, which is what I have here. And when I square this guy, I get him cubed, which goes there. All right. Now the next thing we do is just plug in all this information that we're given down here, and then we're pretty much done. So when we square it, what do we get? We get integral 0 to 1 f squared minus 2 0 to 1 integral f plus 1, that squared. And then we have integral 0 to 1 f minus 1 integral 0 to 1 f cubed dx minus 3. All I'm doing is foiling this stuff out, or using, you know, the Pascal's triangle, whatever it's called. I just remember Pascal's triangle. Minus 1, whatever. So here I'm using, you know, I'm just multiplying everything out and then pushing the integral through using the linearity property. And then what does this guy equal? So integral of f squared is 5. 5 minus 2 times that guy is 2 plus 1, and then you square it. And then this guy, integral of f is just 2, so I have 2 minus 1. Integral 0 to 1 f cubed dx. And then you end up with minus 3 times 5. So I have minus 3 times 5 plus 3 times 2 minus 1. And it looks like I forgot my 1 here, so let me put that 1 there. So I have 5 minus 4 plus 1. That gives me 2 squared, which gives me 4. 2 minus 1 is 1. So now I have integral 0 to 1 f cubed dx. This guy is minus 15. This guy is plus 6. This guy is minus 1. That gives me a minus 10. And now I just move the 10 over. So I have 14 less than or equal to f cubed dx. And that's this problem. So this was a qualifying exam problem. And I spent a long time trying to figure this out, and I just kept getting stuck. And the reason I got stuck was because I knew Cauchy-Schwarz had to be involved somewhere, but this very first step of rewriting it in this way was just not clicking for me. Once I was shown this, everything fell into place. It was somewhat accessible problem, I guess. It's stuff like that that bugs me, you know. Just not seeing this one tiny thing. Like, you can do everything else, but this one tiny thing you can't see ends up hurting you in the end. Anyway, that's number 2. And the last one, I was originally going to do 5 in this video, but I think it's just going to take too much time. So I'm only going to do these at 3 at a time. We have m is a finite measure on some set E. We define rho of fg to be the integral over E of the function minimum, 1, and f minus g absolute value. So whichever of these two values is the smallest, this function takes that value. So it's at most 1, right? And then what do we see? We see that we want to prove the following claim. Fn converges in measure to f if and only if rho of Fn of f tends to 0 as n tends toward infinity. Okay. The reason why I chose this problem for this video is because in the stack of like 80 problems I did, this one was my favorite. And the reason this one is my favorite is because it's not too easy, but it's also not too difficult. Everything here just kind of comes about naturally from doing the problem, and I like problems like that. I think it was also a qualifying exam problem, and it also looks familiar, like I've seen it in a textbook or something. Okay, so since it's an if and only if, we need to assume one direction and then prove the other. So assume that Fn converges to f in measure. So what does that mean? By definition, I've written this definition down so many times. We have that the measure Fn minus f bigger than epsilon is less than epsilon. So that's just the definition of convergence in measure. Now I'm going to denote some things just to make my life a little bit easier. I'm going to define A to be this set. So we have Fn minus f bigger than epsilon, period. And now I need to investigate this guy. So the idea is what I'm going to do is I'm going to write this guy down, and I'm going to bound him above by some epsilon. And since epsilon can be arbitrarily small, I'm going to show that this has to tend towards 0. Okay. So well, I've already used epsilon up here, didn't I? Oh, Actually, you know what? I'm going to choose an epsilon between 0 and 1 here. And I am allowed to do that. You'll see why it doesn't matter if epsilon is huge in this problem. But typically what we want to happen is we want to choose epsilon small, because that ends up being beneficial to us. So I'm going to pick an epsilon between 0 and 1. So I have rho of fn comma f is equal to the integral over e minimum 1 absolute value fn minus f dm. And so what can I do with this guy? I don't really have much to work with, right? They didn't really tell me anything other than we have convergence and measure, and I have this set to play with. So using just properties of integrals, I can split the set up, e, into a and a complement. So that's what I'm going to do. So this is equal to, never know where to put this, integral over a minimum 1 fn minus f dm plus integral over a complement minimum 1 fn minus f dm. And so now I can bound some stuff from above. So we'll start with a. So what do I notice about a? I know that a is this guy. So I know that fn minus f is bigger than epsilon, and that epsilon is between 0 and 1. So what's the most that this guy could be? Well, the most this guy could be is 1, because either fn minus f is between 0 and, between epsilon and 1, or it exceeds 1. If it exceeds 1, then minimum just takes the value 1. So the largest this function could be is 1. So we write integral over a 1 dm plus. Now what about this guy? Well, for this guy in a complement, we know that fn minus f is less than or equal to epsilon. So we can just write in epsilon times the integral over a complement. But epsilon is just a constant, right? It doesn't feel m. It doesn't depend upon your input. So I can pull the epsilon out, and then I just get the measure of a complement. Now I don't know what the measure of a complement is, but I do know that m is a finite measure on e, so it's at most the measure of e, which is some constant. So it's some constant times epsilon, which is just epsilon by another name. And this guy over here is just, that's just a 1, right? So we end up with the measure of a. But what do I know about the measure of a? A is this guy, and it's bounded above by epsilon. So I end up with epsilon plus epsilon times some constant. And that's just epsilon by another name. So just take epsilon close to 0. So I'll write since epsilon positive is arbitrary, this implies that rho of fn comma f tends to 0. Oh, we're not done yet. We're not done yet. But since epsilon positive is arbitrary, we know that this guy has to be tending to 0 when epsilon gets small. And I know I can say that because, remember, this epsilon came from up here when we defined convergence and measure. All right, so now we need to prove the opposite direction. We need to start here and end here. So we'll write the epsilon condition down first. So conversely, we take an epsilon to be sufficiently small. And for this part, we need to use a result that shows up in textbooks. Otherwise, we're not going to get this solved. So this is kind of the reason why I saved this one for last. We need to use Markov's inequality. So apply Markov's inequality. How do you spell Markov? I believe it's this way. Markov's inequality is like a more generalized version of Chebyshev. Chebyshev's inequality shows up in measure theory books a lot. So what does it say? we say that the measure, remember, the goal is to show this guy. So we need to show that this is less than or equal to epsilon. So we have measure Fn minus F bigger than epsilon. That's going to be less than the measure of, how do I want to say this? The measure of minimum 1 Fn minus F greater than epsilon. That's certainly true, because the biggest this could be is 1, and in this case that could be smaller. Okay, so this part's just true by definition. You know, if something is in here, that measure, that set's going to be smaller than that set. So now comes in Markov's, which says that this set, the measure of this thing, is less than or equal to 1 divided by epsilon, integral over e. And then we write the function. So we have minimum 1 Fn minus F dm. But this tends toward 0 as n tends toward infinity. And that's true by assumption, because we assumed that rho Fnf tends to 0. But this, what I've written to the right of my 2 fingers, that's rho Fnf. So that's tending toward 0, and this 1 over epsilon is just some fixed constant. So since this is true for any epsilon, since true for any epsilon fixed, all right, we have that Fn converges in measure to F. I think I did this correctly, but if I didn't, I'm sure someone will correct me. So that's my favorite problem. So I did 3 here. I'll probably do 3 more in the future at some point when I find enough time to get these videos made. I have homework that I'm backed up on, and I really got to get that done because it's due Tuesday. I'm not super worried about it, but I really do need to, you know, do the things that matter most. So I hope you enjoyed this video. I will plan on doing more of these so I can use them as a review guide for the qualifying exam. And yeah, also I want to say we're close to 10,000 subscribers, which is bananas. I did not expect people to actually enjoy watching my stuff. So thank you very much for showing your support, and more content to come. Thank you.